the previous lecture, we have established that for a system of particles, we can work with angular momentum and the angular momentum satisfies the condition that its rate of change is equal to the torque which is applied externally on a system of particles. I showed in the case of a one particle system that this was equivalent to applying the rate of change of momentum is equal to the net external force. We also saw that if dl over dt is equal to tau external and if tau external is 0, this implies that L or the angular momentum is going to be a constant. Let me start this lecture by taking a two particle example and applying this condition to get my answer, and again showing that the result that I get is completely consistent with the momentum equation dp over dt equal to f. So, I would have established through these two examples that it is useful in certain conditions, a particular rigid body rotation, to consider this equation rather than this equation. The example I take is, let me take a rigid massless rod whose one end is fixed at point O and it is free to rotate like this about this point. At the other end of this, I have a mass m2. Let this and this be my x and y coordinates. There is a mass m1 that is travelling in this direction with speed v and it strikes mass m2. What I would like to know is, if mass m1 got stuck with m2, what will be the angular speed of rotation of the system? After all, when mass m1 hits m2, this rod being rigid, it cannot go up and down. The only freedom it has is to move like this. Let me consider the system to be consisting of masses m1 and m2. Then if I look at the rod, the only force that is applied externally on the rod is at this point O, and this gives no torque because the force is not away from the origin. So, about this point O, there is no torque applied, and therefore, if I take angular momentum about point O, it is going to be conserved, and that I can use to calculate the final omega. So, the system I have is this: mass m2, mass m1 coming in with speed v. Let this distance from the x axis be a and let the length of the rod be b. Remember, it is very important that I specify the point O, because angular momentum and torque are origin dependent quantities. So, it is only about point O that the angular momentum is conserved. So, L initial by definition of L is going to be, m2 is not moving, so it does not contribute, only m1 v times a. You can check for yourself, this is equivalent to m1 r1, where r1 is a vector describing the position of particle 1 cross v1, and the direction is going to be into the page. After the masses get stuck and they start moving with speed angular speed omega, L final is going to be, now the masses m1 plus m2 will be moving with speed omega. So, therefore, the velocity is going to be b times omega, and times b gives me the final L final, which is m1 plus m2 times b square omega. Again, the direction being into the plane of this paper. Equating the two, because tau external is 0, therefore, L final and L initial must be the same, and therefore, I should have m1 plus m2 b square omega is equal to m1 v a, or omega equals m1 v a divided by m1 plus m2 times b square, and that is my answer, which I obtained from the conservation of angular momentum. So, let me write this answer obtained from the conservation of angular momentum, and to be very specific about O. Do I get the same answer if I apply my conventional dp dt equals f? Let us check that. So, remember this answer. Okay? If we do that, let us see what happens. There is a rigid rod and m1 strikes it. The only direction this rod can apply a force on m2 is in this direction. Let us say this force is tension T. Since the rod is rigid, it can withstand any momentum change in this direction, and apply an equal and opposite force to make that momentum 0. So, when this particle comes in with momentum p, it is coming in like this. It strikes mass m2. The component of momentum in this direction will go to 0, because this T would be sufficient to make it 0. It is a rigid rod after all. The only component that of momentum that will survive will be this. If I call this angle theta, then this angle is also theta. So, the initial momentum m1 v cosine theta will go to 0 because of this force T applied by the rigid rod, goes to 0, and the only component that will survive, because there is no force in this direction, will be m1 v sin theta, which will be equal to m1 v a divided by b, where a is this distance, as I said earlier, and b is the length of the rod. And this momentum remains the same, but now after the mass m1 gets stuck with mass m2, the mass changes, and therefore, the velocity v prime is going to change, and this is therefore is going to be m1 plus m2 times v prime, where v prime is the new velocity in this direction, and this gives me v prime is equal to m1 v a over b m1 plus m2. So, to recall again, after masses get stuck, this fellow moves immediately after that with velocity v prime, and therefore, omega is going to be v prime over b, which is equal to m1 v a over m1 plus m2 b square, which is the same answer as obtained earlier by applying the conservation of angular momentum. So, the point I am trying to make through these examples is that applying the formula dl over dt equals tau, or its consequence that tau 0 means L is a constant, is equivalent to applying Newton's second law. and therefore, depending on the situation and particularly in rigid bodies, we are going to use this, which is much more convenient to use.